Okay, so we are continuing in 3.4 with properties of continuity. So in the last lecture we learned about how to establish continuity at a specific point, and now we're going to just talk about the continuity of f and g at a specific point as well. And so there's some properties that go along with, if I know that f and g are continuous at a specific point c, then there's some properties that go along with it. And I just have b as, this means that b is an element of the real number system. So this is just some mathematical synonyms. It just means when I use b down here, it's a real number. That's all it means. Okay. So the first thing that we know, so we're going to assume that f and g are continuous at some place here, that's c. So what that means is that if f is continuous, then if I multiply f by some scalar multiple, just meaning any number, no variable, just a number, like 2, a half, square root of 3, then that times f of x is also continuous at x equals c. Like for instance, if I knew that f of x is x squared is continuous at a point, which it's continuous at all of its points, then if I multiply it by a number, say like the square root of 3x squared or a half x squared, it's also continuous at any specific number c as well. Okay. And then also sum and differences. If f and g are both continuous at a specific point, then if I add f and g together or subtract g from f or vice versa, then it holds on to its continuity. Okay. And also if I multiply two functions together, I'm again assuming that f and g are both continuous at x equals c. Then if I multiply the two functions together, that resulting function will also be continuous at x equals c. And of course, the same thing for the quotient. It's just that, of course, and usual fashion, that it's continuous assuming that g of x is not equal to 0 at x equals c. So meaning g of c cannot be 0. Okay. Otherwise, it will be continuous. So if I plug in, if f and g are both continuous at x equals c and g of c isn't 0, then f divided by g is also continuous at x equals c. I know it seems kind of basic, like of course it would be, but not everything in math works that way, so we always have to define everything very carefully. Okay, so let's talk about some functions that have specific continuous properties. Okay, and so these are functions that are continuous at every point in their domain. So we have to remember, right? This is why I've stressed this so much, is that it's continuous at every point in its domain. And so polynomials, since the domain is all real numbers, it's continuous everywhere. I think we've already said that before, but I'm just re-emphasizing. Right? Polynomial functions are continuous everywhere. Rational functions are continuous upon their domain. Right? So a rational function is a polynomial divided by a polynomial. Right? I'll just call it n of x over d of x. And it is continuous everywhere on its domain. It's discontinuous, right? So because d of x equals 0 is not in its domain. So it's continuous everywhere except for that. So it's continuous at every point in its domain, because any places that would make d of x equal to 0 would not be part of the domain of the rational function to begin with. And the same with radical functions. They're continuous everywhere that they're defined on their domain. So if I had f of x is equal to the square root of x, right, that's not continuous on the entire new real number system, because I know that this has a domain restriction of x is greater than or equal to 0. So, but as long as I stay in x greater than or equal to 0, then I know that it will be continuous. So polynomials, rational functions, and radical functions are all continuous on their domain. As long as I stay in their domain, then everything is very smooth and there's no breaks. Okay, so one more thing that we want to talk about really quickly is the continuity of composite functions. Okay, now we've actually maybe seen a little bit of this previously, but so if I have f of g of c, okay, my c looks a little funny there. If I have f of g of c, and g is continuous at x equals c. So we remember when we're doing composition, we always work from the inside out. So if G, the inside, is continuous at C, meaning it's defined and nice and smooth, then and F is continuous at G of C, meaning whatever I get out when I plug in C into G is part of the domain of F, then F of G of C is continuous at X equals C. Okay, so one of the examples that we did, it wasn't necessarily about continuity, but it was in the composition of functions before. If I have f of x is the square root of x, and I have g of x is equal to x squared, then if I did g of f of x, right, this is an example of where it wouldn't be continuous. So if I had, let's see, if I did g of f of negative 2, okay, so this would fail my statement up here, because here f of negative 2 is not continuous there, and so this would fail. However, if I went in the opposite direction, if I did f of g of 2 here, then that means, okay, so g of 2, it's continuous there, and so g of 2 is 4, right? So then as long as f of is defined when x is 4, then this is continuous there, right? And it is. So I would get out 2 here. So as long as, right, when I put the inner thing in, this is continuous here, and my outer function is defined at that point, then my composition of functions will hold its continuity.